What if I told you that right now, as you're reading this, time is moving slower for your feet than for your head? What if the solid chair you're sitting on is actually 99.9% empty space? And what if the universe itself? Well, that's where things get really weird. Stephen Hawking spent his life uncovering secrets so mind-bending that they sound like science fiction. But here's the thing, they're not fiction, they're reality. And by the end of this summary, you'll understand why Einstein called quantum mechanics spooky, why black holes aren't actually black, and why the Big Bang wasn't really a bang at all. But first, let me ask you something that might keep you up tonight. If time itself had a beginning, what came before the beginning of time? Stick around, because the answer will change everything you thought you knew about existence. What first made you curious about how the universe began? Share your thoughts in the comments before diving in. A brief history of time. Summary: Stephen Hawking's Guide to Understanding the Universe. Introduction. Why a brief history of time changed everything. Stephen Hawking's A Brief History of Time tackles the biggest questions humans have ever asked. Where did we come from? How did the universe start? What does the future hold for everything we know? Published in 1988, this groundbreaking book became one of the best-selling science books of all time. But it's also often called the most unread bestseller. Why? Because while Hawking was brilliant at explaining complex physics, the concepts can still feel overwhelming. That's where this summary comes in. We've broken down Hawking's most important insights into simple, everyday language that anyone can understand. Think of it as your friendly guide to the universe's greatest mysteries. For a visual timeline of the universe, check out NASA's Big Bang Timeline infographic. This book is for you. You've always been curious about how the universe works but found physics intimidating. You want to understand concepts like black holes, time travel, and the Big Bang without getting lost in equations. You're looking for a mind-expanding read that will change how you see reality. You enjoy books that make you question everything you thought you knew about existence. Life gets busy, and diving into complex physics isn't always practical. That's why we've distilled Hawking's masterpiece into the key insights you need to understand our universe. About Stephen Hawking, the mind that revolutionized physics. Stephen Hawking, 1942 to 2018, was a theoretical physicist and cosmologist whose groundbreaking work transformed our understanding of black holes, time, and the origins of the universe. Despite being diagnosed with ALS at age 21, he defied all odds to become the Lucasian Professor of Mathematics at Cambridge, the same position once held by Isaac Newton. His best-selling book, A Brief History of Time, made complex physics accessible to millions and turned him into one of the most influential scientists of the modern era. Think about that for a moment. While his body gradually lost the ability to move and speak, his mind soared to the furthest reaches of the cosmos. Hawking's story teaches us something profound. The human spirit's capacity to transcend physical limitations is as infinite as the universe he studied. His determination to understand reality, despite facing seemingly impossible odds, mirrors humanity's own quest to comprehend our place in the cosmos. Story Shot 1. Why scientific theories are humanity's greatest tools. Ever since the dawn of civilization, people have not been content to see events as unconnected and inexplicable. They have craved an understanding of the underlying order in the world. Stephen Hawking. Imagine you're trying to predict tomorrow's weather. You could guess randomly, consult ancient folklore, or use modern meteorology. The difference in accuracy is staggering. And it all comes down to having a good theory. The problem: living in an unpredictable universe. For most of human history, we lived at the mercy of forces we couldn't understand. Earthquakes, eclipses, and diseases seemed random and terrifying. People created myths and superstitions to explain these events, but these stories couldn't help them predict or control what happened next. The solution: building theories that actually work. Hawking explains that a scientific theory is much more than a guess or opinion. It's a model that accurately describes observations and makes definite predictions about future experiments. Think of it like a map. A good map doesn't just show you where you are. It helps you navigate to where you want to go. A powerful theory must meet two crucial criteria. It must accurately describe observations, and it must make testable predictions. Newton's theory of gravity perfectly explained why apples fall down and why planets orbit the sun. More importantly, it allowed scientists to predict exactly where planets would be months or years in the future. The application: how theories transform our world. Every piece of technology you use exists because someone developed and tested theories about how the world works. Your smartphone's GPS system works because engineers applied Einstein's theories about time and space. The Internet exists because scientists understood electromagnetic theory. Quick refresh. Scientific theories help us predict and control nature by accurately describing observations and making testable predictions. Now let's see how Newton's laws made the universe predictable. Story Shot 2. Newton's revolutionary insight: everything is always moving. Before Isaac Newton, people believed objects naturally wanted to be at rest. This intuitive understanding created a massive problem for early astronomers. If objects naturally come to rest, why do the planets keep moving? The solution: motion is the natural state. Newton's breakthrough was radical. Objects don't naturally come to rest. Instead, they naturally keep moving in straight lines at constant speeds unless something interferes with them. This principle flipped physics upside down. When you're in a car traveling at highway speed, you don't feel like you're moving until the car brakes or turns. Newton realized that this is actually the natural state of all objects in the universe. The reason things seem to naturally slow down on Earth is because of friction and air resistance. Newton turned falling apples into the blueprint for the entire cosmos. Newton's most stunning realization was that the same force making apples fall also keeps planets in orbit. The moon is constantly falling toward Earth, but it's also moving sideways fast enough that it keeps missing our planet. It's like throwing a ball so hard that the Earth curves away beneath it faster than it can fall. Quick refresh. Newton showed us that motion is natural and gravity is universal. Objects don't want to stop. They keep moving unless something stops them. This insight made the universe predictable and laid the foundation for modern science and technology. Story Shot 3. Einstein's mind-bending discovery: time isn't what you think. Here's a question that might keep you up tonight. What if time isn't the same for everyone? What if your watch could literally run slower or faster than someone else's, and you'd both be correct? The problem: light broke Newton's perfect system. Newton's laws worked beautifully for almost everything, but they had one major problem: light. When scientists measured the speed of light, something impossible happened. No matter how fast they moved toward or away from a light source, they always measured exactly the same speed: 186,000 miles per second. Always. Without exception. The solution: space and time are connected. Einstein's solution was radical. Space and time aren't separate, fixed things. They're woven together into a single fabric called space-time. And this fabric can stretch, compress, and bend. The speed of light is constant, but time itself can change. Time doesn't flow like a river. It stretches, bends, and slows depending on where you are and how fast you're moving. The application: time dilation in your daily life. This affects technology you use every day. GPS satellites orbit Earth at about 8,700 miles per hour and experience weaker gravity than we do on the surface. Both effects cause their clocks to run differently than clocks on Earth. Without correcting for these time differences, GPS would be off by several miles within hours. Quick refresh. Einstein showed us that space and time are connected and flexible. Time can slow down or speed up, depending on how fast you're moving and how strong the gravity is around you. This isn't just theory. It affects the technology we use every day. Story shot 4. The Quantum World, where reality gets weird. If Einstein's relativity seemed strange, quantum mechanics will make your brain hurt in the best possible way. Welcome to a realm where particles can be in multiple places at once, where the act of observation changes reality, and where uncertainty isn't a limitation. It's a fundamental feature of the universe. The problem: the atomic world doesn't follow our rules. When scientists tried to measure the exact position and speed of subatomic particles, they hit an impossible wall. The more precisely they measured a particle's position, the less precisely they could know its speed. This wasn't a problem with their instruments. It was a fundamental feature of reality itself. The solution: embracing uncertainty as natural. Werner Heisenberg discovered the uncertainty principle. You cannot simultaneously know both the exact position and exact momentum of a particle. Instead of thinking of particles as tiny billiard balls, quantum mechanics describes them as probability clouds. An electron doesn't have a specific location. It has a range of probable locations. The famous double-slit experiment demonstrates this perfectly. When you shoot individual photons through two parallel slits, they create an interference pattern as if each particle went through both slits simultaneously. But if you try to observe which slit each particle goes through, the interference pattern disappears. The application: quantum effects in your technology. Quantum mechanics powers much of modern technology. Your smartphone's processor relies on quantum effects to control electrons through transistors. LED lights, lasers, and MRI machines all depend on quantum principles. Quick refresh. At the smallest scales, particles don't have definite positions or speeds. They exist as clouds of probability. You can't measure everything about a particle precisely because precision itself has limits built into nature. If observing reality changes it, what does that mean for how we live our lives? Tell us what you think in the comments. Story shot 5. Black holes, the universe's ultimate mystery. Black holes are regions of space where gravity becomes so strong that nothing, not even light, can escape. For decades, they seemed like mathematical curiosities. Today, we know they're real and they're everywhere. The problem: when stars run out of fuel. When massive stars, those more than about 25 times the mass of our Sun, run out of nuclear fuel, something extraordinary happens. The collapse doesn't stop. Gravity becomes so strong that it overwhelms every force that might resist it, crushing the star's matter into a point of infinite density called a singularity. The solution: understanding gravitational collapse. Around this singularity, space-time becomes so warped that it creates a boundary called the event horizon. Cross this boundary, and you can never escape, no matter how fast you travel. Even light gets trapped beyond the event horizon. Hawking made a revolutionary discovery. Black holes aren't perfectly black. Due to quantum effects near the event horizon, black holes actually emit radiation, now called Hawking radiation. This means black holes slowly evaporate over time. The application: black holes shape the universe. Supermassive black holes sit at the centers of most galaxies, including our own Milky Way. As matter spirals into them, it creates some of the brightest objects in the universe. In 2019, scientists took the first direct image of a black hole's event horizon using the Event Horizon Telescope. Black holes are not the cosmic vacuum cleaners of popular imagination. They're more like cosmic recycling centers, transforming matter and energy in ways that help shape the entire universe. Do you find black holes fascinating or terrifying? Drop a one-word answer, fascinating or terrifying, in the comments. Story Shot 6. The Four Forces That Rule. Everything. Everything that happens in the universe results from just four fundamental forces. Gravity is the weakest force, but has infinite range and affects everything with mass. Electromagnetic force affects all particles with electric charge and is responsible for light, electricity, and chemical bonds. Weak nuclear force operates only at short distances and causes radioactive decay. Strong nuclear force is the strongest but operates only at extremely short distances, binding atomic nuclei together. The most exciting discovery is that these forces aren't completely separate. At extremely high energies, some merge into unified forces. Scientists have already unified electromagnetic and weak nuclear forces. The ultimate goal is a theory of everything that describes all interactions with a single set of equations. Quick refresh. Four fundamental forces govern all interactions in the universe. At very high energies, these forces may unify into a single interaction. Story Shot 7. The Big Bang. How everything began from nothing. Even if there is only one possible unified theory, it is merely a set of rules and equations. What is it that breathes fire into the equations and makes a universe for them to describe? Stephen Hawking. The Big Bang isn't just the beginning of everything we can see. It's the beginning of space and time themselves. The solution. Two models for cosmic creation. The hot Big Bang model describes the universe starting from infinite density and temperature. Space itself began expanding rapidly, carrying matter and energy along with it. Within the first few minutes, the first atomic nuclei formed. After 380,000 years, the universe cooled enough for the first atoms to form, making it transparent for the first time. The inflationary model adds that in the universe's first tiny fraction of a second, space underwent exponential expansion. The universe grew by a factor of at least 10 to the 26th power. Imagine a grain of sand becoming larger than a basketball. The evidence all around us. The Big Bang is supported by multiple lines of evidence: cosmic expansion, distant galaxies moving away from us, cosmic microwave background radiation, the afterglow of the Big Bang, and element abundances that match predictions perfectly. The Big Bang wasn't an explosion in space. It was an explosion of space itself, creating not just all the matter and energy in the universe, but the very stage on which cosmic history would unfold. Which idea blows your mind more? That the universe had a beginning, or that time itself began with it? Tell us below. Mental models, transferable frameworks. Hawking's concepts provide powerful mental models for daily life, scale-dependent reality. Different rules apply at different scales. Newton's laws work for everyday objects, but break down at very high speeds or very small scales. In business, strategies that work for small companies often fail for large corporations. Uncertainty precision. Trade-off. You can't know everything precisely simultaneously. In project management, you can control scope, timeline, or budget precisely, but not all three at once. Emergence principle. Complex behaviors emerge from simple rules. The four fundamental forces create all cosmic complexity. In organizations, culture emerges from simple behavioral norms. Implementation guide. Today, watch NASA's 3-minute cosmic expansion video. This week, notice how physics underlies your daily tech: GPS, WIFI, MRI. Ongoing. Practice thinking in scales. From quantum to cosmic. To reframe problems. Final summary. 8 key insights. Stephen Hawking's A Brief History of Time revolutionized how we think about the universe. 1. Scientific theories are humanity's greatest tools for prediction and control. 2. Motion is natural. Objects keep moving unless something stops them. 3. Time and space are flexible. They can stretch, bend, and slow down. 4. Uncertainty is fundamental. You can't know everything about particles simultaneously. 5. Black holes are cosmic recycling centers that shape galaxies. 6. 4 forces govern all interactions in the universe. 7. Time has direction, from order to disorder. 8. The universe has history. It began with the Big Bang 13.8 billion years ago. These insights provide new ways of thinking about uncertainty, complexity, and change in your own life. When you understand that the universe operates on principles that seem impossible from our limited perspective, it becomes easier to imagine new possibilities. Take action. Share your cosmic journey. Share your favorite insight from Hawking's work on social media and tag at StoryShots. Which concept challenged your thinking the most? The next time you look up at the night sky, remember that you're seeing the universe's history written in starlight. The carbon in your body was forged in ancient stars. You are literally made of star stuff, connected to the cosmos in the most fundamental way possible. New to StoryShots? Get the free app to access the audio, PDF, and animated versions of A Brief History of Time and hundreds more. Featured by Apple, Google, and The Guardian. Welcome to your cosmic journey. The universe is waiting for you to explore it. Ready to dive deeper? Get Stephen Hawking's A Brief History of Time and begin your exploration of space, time, and everything in between.